Okay, let's get started. Welcome, everyone. So I said that today's class was going to be on different proof techniques, invariants, monovariants, and inequalities. And I'm actually going to move inequalities to next class, where we're also going to talk about polynomials and algebra. This class is just going to be about invariants and monovariants. So let's start out with some course announcements. First, a reminder that the problem set is due on Friday. That is at the end of the day, Montreal time, so 11:59 p.m. Montreal time on Friday. That should be submitted by My Courses. There should be a way to submit your work through My Courses. If you do not have access to My Courses because you are an auditor who is not associated with McGill, then you should just email directly to me and to Vincent, and we'll look at it that way. So there should be a template again for if you are using LaTeX for the problem set. It is not required to use LaTeX for this first problem set, but it is encouraged to use LaTeX. And if you're using LaTeX, you can use the template files, which are available both on the Slack and on the My Courses page. I also remind people to post in the Slack if you're looking for collaborators. Collaboration is encouraged. It's great if you don't know what to do on a problem. Go post in the Slack saying, I'm looking for a collaborator on this problem, and you can start a separate conversation. You can direct message people on the Slack. That's what it's for. Please don't post solutions to the problems in the Slack, though. Okay. And then one more reminder, which is that my office hours are right after this class. I also have office hours on Friday morning, but I have office hours right after class. So just stay in the Zoom room if you want to chat about the problem set, if you have questions about that, or really anything else, or if you just want to talk about math or any of the things that I'm interested in. Great. Are there any questions about anything? I'll take that as no, but feel free to ask them during the class as usual. Okay, let's not go back to that problem. We will get to it, but we're going to start out with an easier problem. But before I get to the problem, there is a question. In the Slack, can we ask questions like, should I be using strategy X to solve problem Y? If you are asking questions about the P set, you should do that in a private message to me or in a thread with your collaborators. You shouldn't do it overall for the group because that's sort of giving hints to the rest of the group or alternatively confusing the rest of the group. Really good question. So don't be specific about things, but you can say, I'm looking for a collaborator to help on problem Y. This is just to make it, because collaboration should be really both ways. And the way to do that is for it to be a smaller group, because for a larger group, it's just really hard to do that. That's how I learned this stuff. Okay, so let's get started with the first problem. The numbers 1 through 100 are written on a blackboard. You may choose any two numbers, A and B, and erase them, replacing them with a single number, A plus B. After 99 steps, only a single number will be left. What are the possibilities for that number? Are there thoughts? So let's start out by replacing two of the numbers by their sum. What happens if we would do this operation twice? So we have A and B and C. So then we have A plus B, and then we have C. So we have A plus B plus C. So we replaced A plus A and B and C by A plus B plus C. So we're going to get the sum of three numbers. In general, if we had a plus b plus c and we did this same thing with d, we replace a plus b plus c and d with a plus b plus c plus d. So in general, as I see a lot of people are writing in the comments, no matter the order in which we combine the numbers, we will eventually be left with the sum of all of them. This is a simple situation, and we'll come back to this in a moment with a slightly more complicated twist to it. But it's an illustration of a general principle called invariance. So an invariant is just a quantity that remains unchanged. Now, there are various different situations in which the term invariant is used. So for example, it's used in programming in a different context, and I'm not going to talk about like loop invariance, but it is in every context, it means a quantity that remains unchanged. In the particular situation we'll be looking at today, we'll be looking at it as a general problem-solving technique. And the goal is to identify, the way that we do this problem-solving technique is to identify an invariant, to calculate its initial value and conclude that its final value has to be the same. So if you have some process that's happening, you're doing some algorithm, and you find an invariant, well, you know that whatever it was at the start of the algorithm is going to be the same as it is at the end because it's an invariant and it doesn't change. So in the case of the previous example, we had the sum of all the numbers on the blackboard. And at every point, the sum of the numbers on the blackboard wasn't changing. So if you replaced a and b by a plus b, the sum of all the numbers there wasn't changing, even though the number of numbers there was changing. So we could show that there was an invariant, and we'll see a formal proof. But first, when is this useful? It's first useful in working out what the final state has to be based upon the value of the invariant. That sometimes is enough to tell you what the final state is. In this particular case, we knew there was one number left. And so since the sum of the numbers on the blackboard had to be constant, the final number had to be just equal to the sum of all of the numbers at the start. Sometimes it's more important, what we actually want is to show that some final states are impossible because the invariant has a different value. And we know that the invariant can't change value because it's by definition an invariant. So we'll see some examples of problems where we're trying to prove that the final state is not possible because of the invariant. So with all of that said, let's take a look at a proof of problem one. Just so you can get a sense of like what an invariance proof might look like. Though there are different ways to write this. Observe that the sum of all the numbers on the blackboard is invariant under the operation described, since we are replacing two numbers by a single number that is their sum. Therefore, the final sum must be the same as the initial sum, because it's invariant. And hence, if there is a single number left, that number must be the sum of the original values. And then remember, we had this nice formula for working out what the 100th triangular number is, which is that. Are there questions about this problem or in general about the technique of invariance? But we'll see a couple more examples soon. Any questions so far? Okay, let's see a slight variation on this. What if a and b get replaced by a plus b minus 1 at each step? So our invariant before was the sum of all of the numbers. So how can we change that to make something that is invariant under the new operation? What would the new invariant be? Something that doesn't change at each point, in each move. And I see a lot of people have worked out what the final answer is going to be. So it's not going to be the sum minus 1, because the sum, when you you take 1 away at each step. So you're going to have to sort of add 1 back in at each step. Yeah, exactly as somebody is suggesting. You're going to have the sum, and you're going to have to add in something to compensate for the fact that each step takes away 1 totally from the sum. The sum of the numbers plus the steps already taken is an example of an invariant here. Because each step, you're adding 1 to the number of steps, and you're taking away 1 from the sum of the numbers. So let's see a formal proof. And this is a little bit less simple. We claim that the sum of the numbers on the board plus the number n of operations performed is invariant throughout the process. It's always good to define terms just to make it easier to write your equations and show that things are working as you want them to. So the operation replaces 2 numbers by 1 less than their sum. So the overall sum s decreases by 1 each iteration. Each operation also clearly increases n by 1 because n is just the number of operations. So if you've decreased s by 1 and increased n by 1, then s plus n stays constant. Therefore, the final value of s plus n must be the same as the initial value. Initially, what's the value of our invariant initially? Well, the invariant is now s plus n. So s was just, again, the sum of all the numbers, and n is just 0. So the value of the invariant is the same as the value of the invariant before. However, at the end, what we're going to have is instead of s is equal to this invariant, we're going to have s plus n is equal to this invariant. And after a certain number of operations, 99 of them specifically, we must have that the invariant, which is 5050, is equal to s plus n, which is in this case s plus 99, and therefore s is equal to 4951. As only 1 number is left, this number must be that invariant, 4951. Any questions about this? So there's a question about whether, what you can say is obvious. It's a really good question, and there isn't a clear answer. So I'm writing this I'm spelling it out a little bit more than you might need to for a proof, but err on the side of making it a little bit too clear, because you can read a lot of proofs by professional mathematicians or computer scientists who are saying it's obvious that, and then in the best case, you can understand what they're saying. In the bad case, you don't understand why it's obvious and you feel stupid and you don't get their proof. And so they messed up. In the worst case, they write it's obvious because for something that is actually false. And this has happened in published papers where mathematicians have said it's obvious that blah, 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 but it turns out that that was not actually true. And occasionally you have somebody who says it's obvious because they don't know how to prove it themselves, and they hope that the reader will work out how to prove it or will just gloss over it. So just try to really only write it's obvious if you really think it's obvious. But there isn't a hard and fast rule. Good question. Yeah, you can also say it is therefore trivial that. That's mathematician speak for it's obvious. Let's look at another problem. This is a classic for invariance. 2 opposite corners are removed from an 8x8 chessboard. Is it possible to cover it with 1x2 dominoes? So here you see an example of the chessboard with the corners removed and a domino that you could use to cover some of the squares. But you're going to need a bunch of the dominoes. The dominoes can't overlap, and they can't cover anything but the chessboard. Those of you who have been thinking about the problem set might recognize, might have thought a lot about chessboards and pieces. The color doesn't matter. The domino can cover any tile. So what would be the first thing you would do? For example, probably the first thing that you did when you looked at the problem on the P set. At least one of the things that I would do. Like, you know, does it seem like it might be possible? Like, what's the first cut that you could take to work out whether it might be possible? You might just try some examples, yes. You might try some examples. I'm not going to do that, but feel free to do that. That is a very good strategy. That's probably the best strategy. Yes, reduce the problem size and try some examples. Two by two wouldn't work in this case. Yeah, so I was actually suggesting something different, but I think you came up with the right answer. Reduce the problem size is just the correct thing to do. That's what you should have done on the homework. And yeah, it's a good idea. Just play around with it. Now, in this case, what I would probably do, since I'm trying to work out whether it's possible, instead of on the homework where I'm trying to show it is possible, but since I'm trying to work out whether it's possible, is I would probably look at the number of squares. So does that help here? If it's not even, we're in trouble. Exactly. There are two squares for each of the dominoes. So we're going to be covering an even number of squares by these dominoes. Unfortunately, the total number of squares on a chessboard is 64. And so you've taken away 2, which means that you're going to end up with 62, which is even, unfortunately. So is there anything else we can use? Yeah, so each domino is going to cover 2 adjacent squares. So it's going to have 1 white and 1 black. We don't know exactly where they're going to be. So it could be white and black, or it could be black and white, or white and black like this. Or, you know, there could be many ways. But since they're next to each other, the squares are going to be 1 white and 1 black. How does that help us? There was a question about the number of pieces per row being even. It's a good thought, but it's tricky because a vertical domino could go up. It could, like, you could rotate the domino so that it isn't in just 1 row. It could be in 2. Yeah, so we can count sort of how many white and black pairs there are, how many white and black squares there are, because we know that since every domino covers 1 white and 1 black, the total number of squares is going to be the same number of white and the same number of black covered. Is this okay? Yeah, it's not good because there are 30 black and 32 white squares. So it's not going to be possible to have an even number, to have the same number of white and black squares covered by dominoes, which means that the dominoes are just never going to work. We don't know exactly, like, there isn't a particular, we aren't saying they fail because we tried all the possibilities. This is just super swift and super slick. No matter how we place the dominoes, they're going to cover the same number of black and white squares. That's our invariant, or the difference between the number of black and white squares covered is our invariant. And since the difference starts out at 0 and needs to be 2, then we're done. Other questions? This is an example of using an invariant to work out that a certain thing is not possible. This is very common. This is not a formal proof. I'm not actually going to do a formal proof, but feel free to write that up or discuss it or ask me for a formal proof. It's very close to a formal proof. We would be leaving out things like aha. And we would leave out the first idea, which didn't work, just counting the number. Yeah, so here the invariant, you don't necessarily, not every invariant proof needs to be sort of stated as an invariant proof, but in this case, I would call the invariant the number of black squares which are covered minus the number of white squares which are covered by dominoes as you put more dominoes on. As you add a new domino, the number of black squares increases by 1, the number of white squares increases by 1, so that difference stays constant. It starts out at 0 because there are no squares covered at all. And it has to end up being, in this case, -2, number of black minus number of white. Since it can't change each time we place a new domino, then it is going to be, then we have a contradiction. Okay, let's move on to another problem. And this is going to be, I'm not always going to provide the complete formal proofs of everything, just so that we can get through more problems. I'm going to try to give you formal proofs where I think there's a new idea or something like that that needs to be shown. Here's a problem. You're given a 100 by 100 array of lights. You can flip all the lights in any row or any column so that any lights that were turned off get turned on and vice versa. Initially, only one light in the grid is on. Can you flip the rows and columns in such a way that all the lights are turned on? So if we think that it's, if we think that there's a solution, we might try to come up with an algorithm. If we think that there isn't a solution, it's probably a good idea to try to come up with an invariant. An invariant because we know the starting condition of the grid of lights, and we know the final condition. If we can prove that something doesn't change, but the invariant has a different value at the start than at the end, then we'd be done. What's a good idea to start out with? We have this 100 by 100. Yeah, try a smaller number, a smaller number of rows and columns. Hopefully the same thing is true for a 4x4 grid. Let's see. There, I just put a 1 for the light that's on, just picked a random place for it. Okay, let's try flipping some stuff. Okay. Let's try, I've just flipped all this entire column. So this went off, all these went on. Did another couple of moves. Here, to get from here to here, flipped this whole column. Then to get to the next one, flipped this row. So these two went off and these two went on. Anything that we notice? Yeah. So we seem to always have an odd number of ones. We started out with 1, then we get 3, now we have 7. And then we end up with however many this is. This is also 7. Interesting. Is this always true? And if so, why? Try a small example, find a pattern, see if it's true. Is it true just even for the 4x4 grid? In response to a question, an invariant about there will always be a row or column in which there is both a 1 and a 0. I think that that is true but it is not, it will probably not be an easy invariant to prove. Why is this always true about the odd number of ones? So it's not going to have to do with where the location of the one is, hopefully. So if we flip a row or a column, let's look at the change in the number of lights in that row or column. So if we had 0 lights on before, then we're going to have 4 afterwards because all of them go on. If we had 1 light on, then we're going to get 3 afterwards. 2 and 2, 3 and 1, 4 and 0. So you'll notice that the difference between these two is always even. So we're always changing the number of lights, in the row or column that we flip, by an even number. So that means that if we start out with an odd number of ones, as we did before, we're going to always have an odd number of ones. Is this true for a 100 by 100 grid too? If we start out with an odd number of ones, are we always going to have an odd number of ones? Yes, we are. And that's because whenever we change a row or a column, we're changing it from n to 100 minus n. And the key point here is that n and 100 minus n are either both even or both odd. So we're never going to change the parity of the total number of lights. If you haven't seen that word, parity is just whether it's even or odd. So if the total number of lights starts out as even, it's going to stay even. If the total number of lights is odd, then it's going to stay odd. And that's because each time we flip some lights, we're only changing the total number of lights by an even number. We don't know exactly what that even number is, but we're changing it by some even number. So what does that mean? How do we finish the problem? We need to look at, we have this invariant, which is whether it's odd or even, that stays constant. Yeah, we need to look at the starting number of lights. We started with 1 light on, so we're always going to have an odd number of lights on. But we're trying to have an even number of lights on. We're trying to have all of them on. And a 100 squared is even. So we can't get all the lights on. Done. See how much faster this is than like trying to go through all the possibilities, and you could easily end up with such nasty casework here. Just by finding an invariant, it's super slick, super fast. Other questions? Okay. Let's move on to the next problem. Oh, and could we have used induction? Maybe. I'm not sure how we could have used induction. Ultimately, an invariant, there are similarities between invariance proofs and induction. And yeah, so maybe in that case, I don't know. I think invariance, like think about it as an invariance problem, is probably the easiest way. Let's take a look at this problem. This is going to be moving into the next section. So maybe slightly different methodology here. In the Parliament of Fredonia, certain pairs of members are enemies with each other. Each member has a maximum of 3 enemies. Prove that the House of Parliament can be separated into 2 houses so that each member has at most 1 enemy in their own house. This is obviously why, for example, the UK has 2 houses of Parliament. Each person has 3 enemies at most. We're trying to split the people into 2 groups so that they only have 1 enemy in their group. At most 1 enemy, maybe 0. Thoughts? How would we start out with this? Yeah. Let's try just like seeing what we can do. What could go wrong if we tried separating just into 2 houses? We could try a small example, and probably if it were me, I would actually be working with a small example. But since just because of the pedagogy here, let's just imagine it without any particular diagram of the example. Yes, enemyship is mutual, to answer the question. If I am enemies with Fred over there, then Fred is also enemies with me. Yes, let's try, like, what could go wrong? Suppose you just like randomly separated it into 2 houses. What's the problem? I mean, clearly a random partition is not going to work. Yeah, you could have even 3 enemies in your house if random. Certainly, like, suppose that there's somebody with at least 2 enemies in their own house. Like, you've messed up. This partition didn't work. What do we do? Yeah, I mean, it's kind of what you would do, like, if it were actual people, right? Like, you'd be like, go to the other house. Maybe you have fewer enemies there. Does this actually help? Why or why not? Remember that they have a maximum of 3 enemies. So yeah, the problem could be you have like 2 in the other house as well. But you couldn't, right? Like, if you started out with 2 enemies at least in house 1, and you went to house 2 and there were 2 more enemies there, then you would have to have 4 at least enemies. And they have a maximum of 3 enemies. So that particular person is helped, for the moment at least. But yeah, I mean, like, you could have messed up. Like, their enemy in the other house might now have gone over their limit. So we might have a problem. We can keep on doing this, but does this process finish? Can you fix it all, or could we loop back? Like, could we ever, keep on looping around? This does have connections. This does have connections to graph problems. You can visualize this as a graph. So does this ever finish? Can it cycle? Is there anything that we're doing that's sort of making progress that we can think of as like permanent progress? So there's a suggestion that a person can only move once. I'm not sure immediately why that's the case, because potentially their enemies could move as well. You can visualize this as a graph, but I'm not going to do that yet, because we're going to move on to, we're going to have a class on graph theory later on. To answer a question, yes, the enemy of an enemy can also be an enemy. So how many enemy ships in the same house did we have before? I saw a couple of people suggesting this. You started out with 2 enemies in one house, and you went to 1. Now, you might have created another problem. You might have to move another person from the house you moved into. But the number of sort of pairs of enemies, that has decreased a little bit. So you feel like you have made some progress. The total number of enemies within houses is going down each time. And this is going to be an idea which we can use to build a formal proof. Now let me just, before we go into the formal proof, let's talk through the theory of monovariance. Because this is not an invariance problem. This is what's called a monovariance problem. So what is a monovariant? A monovariant is like an invariant, but it can change. So an invariant is something that never changes. A monovariant can change, but it can only change in one direction. It can go always up or always down. If the monovariant is bounded, for example, if it's decreasing but it has to be above 0, then you know that whatever is decreasing it has to stop eventually. So if you have an algorithm that decreases a monovariant, then you know that it can't decrease it forever if the monovariant can't go through 0. As long as the monovariant is making a large enough step size. Like if it's going down by a smaller amount each time, it could asymptote to 0. But suppose it's an integer. When is this useful? It's basically useful in proving that some process terminates. This is the basic use for monovariance. You have an algorithm and you want to show that it has to stop. And you find a monovariant and you show that it's bounded, and that since it's bounded, it can't keep on decreasing or increasing forever, and so the process has to stop. Finding the particular state in which a process terminates can also be a use for a monovariant. So if you know that the monovariant has to be sort of pushed all the way to its minimum or its maximum, then you can actually understand something about that final state that it gets to. And a quick note, you have to be careful that your monovariant is actually going strictly up or down, rather than just staying the same sometimes. It's okay if your monovariant stays the same sometimes, but you have to show that it is going to go up or down eventually after enough moves. Otherwise, if your algorithm could keep your monovariant the same, then it could just be an invariant, and the algorithm might not stop. It might just go down to 0, but then keep on working, and the monovariant stays at 0. Anyway, that's sort of a technical point. With all of that said, let's go back and write a formal proof of the previous problem. So we're going to describe an algorithm for separating the two houses so that each member has at most one enemy in their house. We're going to start, as we did, by initializing the houses randomly. And we're going to, remember our idea for an interesting quantity here was the total number of enemies within a house. So let E1 be the number of pairs of enemies in house 1, and E2 the same thing for house 2. So we're going to perform this operation, which we talked about before. If there is any member who has more than one enemy in their house, move them to the other house. And we claim that each such move strictly decreases the sum E1 plus E2. The word strictly being important there, it has to actually decrease it by at least 1. It can't just keep it the same. So consider performing such a move. Without loss of generality, you're moving a member from house 1 to house 2. Remember, again, without loss of generality is like a math speak it's proof speak for symmetry. It's just the same if you were moving from house 2 to house 1. So just suppose it's house 1 to house 2, just labeling. Now, we know that M had at least 2 enemies in house 1, so E1 is going to decrease by at least 2. Now, because M had at most 3 total enemies, they can have at most 1 enemy in house 2. And that means that E2 could increase, but it's going to increase by at most 1. The number of new enemies that you make inside a house is going to go up by at most 1. But that means that the sum of them is going to decrease by at least 1, because E1 decreased by at least 2, and E2 increased by at most 1. So the sum is a monovariant. It's going to decrease by at least 1 each move. Now, how do we show that this actually solves the problem? Well, we know that this monovariant is not going to decrease beyond 0, because it's the sum of like enemies, right? Like you can't have negative numbers of enemies. So it can't ever get lower than 0, which means that our process has to stop. And when does the process stop? Like, you could always make a move if there is somebody who has at least 2 enemies in their house. So the process has to stop when there are no more possible moves. And that can only happen if every member has at most 1 enemy in their house. So this is a classic monovariance proof where you have this quantity which has to go down, and you want to keep on making moves, but you can't keep on making moves forever because the process, this number can't go down forever. Are there any questions? Can the monovariant be a real number? So it's trickier if the monovariant is a real number because we'll go into this in convergent infinite series later on. But if you had 1 and you took away 1/2 and you took away 1/4 and you took away 1/8 and you took away 1/16, you could be making it smaller each time, Zeno's paradox, without ever actually getting to 0. So you could do an infinite number of moves. So in that case, you would have to show that it decreases by at least some number. If you have a real number, you can have a real monovariant, but you have to show it decreases by some large amount. You have to show it decreases by at least 1, for example. And then it's fine. Good question. Okay, let's move on to the next problem. A traveler leaves city 1 and goes to city 2, which is the furthest away from city 1. From C2, she travels to C3, which is the furthest away from C2, and so on. Assume there are never any ties for the farthest distance. Prove that if C1 and C3 are different, then the traveler will never return to C1 throughout this process. So let's try an example here. This is going to be pretty quick. I'm just going to give you a flavor for this. So yes, the total distance traveled is an increasing monovariant, but I think that that monovariant is not going to help us. We're not trying to also show that the process is going to terminate. We're going to try to show that the traveler never goes back to C1. The traveler is going to start at C1 and go 100 miles to C2. Let's say. Say that she now goes to C3. How many miles shall we say that the traveler has gone from C2 to C3? Could it be 50 miles? No, it's going to have to be more than 100. Because we know that C1, or else C1 would have been further from C2 and we just go right back to C1. Or to some other city that's even further away. So let's say it's 150 miles. Now she's going to go to C4, and likewise, she's going to travel 200 miles. Could she come back to C1 now? No, why? Yeah, so the distance she traveled last is increasing each time. It's 100, 150, 200. So maybe she could travel 250 miles to get back to C1, but that would be a problem because we knew that when we went from C1 to C2, that C2 was the furthest. If she goes to Cn at any stage, then Cn, the distance she's traveling from Cn minus 1 to Cn, has to have been bigger than the distance she traveled for, and bigger again, all the way up to the first distance that she traveled. But if she ever loops back, then C1 to Cn minus 1, the last distance she traveled, would be greater than C2 to C1, which means that she wouldn't have gone to C2 on the first move. She would have gone to Cn minus 1, or some city that was even further away. There's a question about whether it depends upon the shape she's traveling on, though. No, it actually doesn't depend upon the shape she's traveling. It doesn't matter how distances are measured. That's why I didn't draw a picture. It could be distances along roads, just as long as the distance from between two places is the same as the distance between the places switched. A to B is the same as distance from B to A. The last leg that she traveled is a monovariant here. I don't want to dwell on this too much, because this is not a typical monovariance problem. We're not trying to prove that the process terminates exactly. It's just useful to realize that there are things which are increasing each time. Now, a typical monovariance problem, we would be using this distance is increasing to show that something terminates. Here we're trying to prove something different, which is that we can never get back to C1. But I just wanted to give you a flavor for a different kind of monovariance problem before we get into, we're going to have one more problem that's more of a typical monovariance problem, showing that some process has to terminate. And before I talk about this, I want to talk about a different way of proving monovariance problems. It's an elegant way to write some monovariance proofs. It's called the extremal principle. And it's basically if you need to show that a process ends in some particular way. The way that this works is to find a monovariant and suppose it's as big or as small as it can possibly be. It's reached its maximum or its minimum. Then the way that the extremal principle works is that you have to show that if what you want is not true, then you can make this monovariant even bigger or even smaller, which would be impossible because you assumed that it is the biggest or smallest that it could possibly be. And I'll come back to the question in the chat a bit later. This is going to become much more clear with an example. So let's go back to the Parliament of Fredonia. Okay? So here's an alternate proof. And again, this is every member has a maximum of 3 enemies. Prove you can separate into 2 houses, so you have at most 1 enemy in your own house. Again, let's start it the same way. We'll describe an algorithm for separating to 2 houses so that each member has at most 1 enemy in their house. Start by initializing the houses randomly. Let E1 be the number of pairs of enemies in house 1 and E2 similarly for house 2. Consider the partition into house 1 and house 2 such that E1 plus E2 is minimized. You've minimized the number of total enemies within houses. Remember, that was our monovariant from before. So we showed that every move we made it smaller. And so now what we're going to do is we're just going to say, if we've minimized it, then we can't make any more moves. So we claim that every member has at most 1 enemy in their house. Suppose towards contradiction that this isn't true, that our claim is not true, so that some member has more than 1 enemy in their house. Then we can move them to the other house. By our previous logic, E1, the number of enemies in house 1, the house they started out at, is going to decrease by 2. The number of enemies in the house they go to is going to increase by at most 1. And that means that we've decreased E1 plus E2. But we can't have decreased E1 plus E2 because we assumed that it was minimal. We conclude that we have a contradiction, and so every member has at most 1 enemy in their house at this minimal configuration. So what we did was we said, we're trying to find a particular situation. Suppose that our monovariant is minimized. If it's not minimized, we can make a move that makes it smaller. which is sorry, if we're not at the place we want, then we can move this monovariant even smaller, but we can't move it even smaller because we assumed it's minimized. So this is just a more elegant way to formally prove a problem in the same way as you could prove it with a normal monovariance proof. It's generally not going to, like, it's a way to think about the proof of the problem, but it's basically just a monovariance problem in disguise. Let's see another example of this. Given n red points and n blue points in the plane, so in 2 dimensions, drawn on a piece of paper, show that we can draw n non-intersecting line segments, each having 1 red endpoint and 1 blue endpoint. We just need to connect up some of the red points and all of the red points with all of the blue points, pair them up so that there aren't any crossings. Any ideas? How can we start out? What's the typical way to start out for just exploring a problem? Yeah, let's just start with a small case. Let's try n equals 3. Here's a bunch of points. I connected them in some way. It doesn't work. There's an intersection. What can we do? Yeah. So as some people are suggesting, let's just try uncrossing them. So red and blue, let's make red and blue, red and blue. Do the other pair. Darn. We got another crossing. That crossing didn't even exist before. Let's try uncrossing that one. Okay, that worked. But does this work in general? We have an algorithm which we're thinking might be able to solve this problem. We might be able to get no crossings. We need to show, again, that it can't cycle. We need to show the process has to terminate. There's a comment that it might be exponential. It might take a long period of time. We don't really care about how long it is. We just want to show that it terminates. There's a question about whether we can use the same red point for all lines. No, we have to pair them up. I realized that the problem didn't actually say that, so that was my fault in stating the problem. They should be paired up. Is there anything that we can do to show that this process terminates? Let's go back here. Anything that's interesting about what's happening when we're making this move? Uncrossing could lead to a lot more crossings. So if we're looking for a monovariant here, it's not going to be the number of crossings necessarily. The number of crossings could increase or decrease. Is there something that's increasing every step or decreasing every step? We have a process that we'd like to show terminates, so it's a very good candidate for a monovariant. Again, here is our operation. Yeah, so there's something about distance. It seems like things are shorter when we uncross them. Like the length here, it seems inefficient in some sense to do a crossing. If we're trying to connect things, it should be shorter to do this. So maybe the sum of these lengths is shorter than the sum of the lengths before we uncross them. How can we prove this? Here's a formal proof. And this is going to be our final thing for the day. Consider the matching between the red and blue points. I'm going to do this as an extremal principle proof. So we have a monovariant, and we're going to show that we're going to assume it's as small as possible and show that each move makes it even smaller. Consider the matching between the red and blue points such that the total length of segments is minimized. We will show that no crossings can occur. Suppose towards contradictions that there are two segments that do cross, AD and BC, where A and B are red and C and D are blue. And we're going to try to show that if we uncross them, then we get a lower total length of segments. So this is what happens if they're crossed. This is what happens if they're uncrossed. We have to show that uncrossing them reduces the total length of the segments. How can we do this? Why is this true? Ptolemy's theorem is overkill for this, and Ptolemy's theorem is about cyclic quadrilaterals, but good idea. It is indeed something less fancy than that. It is indeed the triangle inequality, as a few people are suggesting. So the triangle inequality says that if you're in a triangle, two sides add up to more than the third side. It's sort of intuitively obvious. Two sides have to always be more than the third side. And so in this case, what does it mean? It means that PA plus PC is greater than AC, and PB plus PD is greater than BD. So we can just write those out. But what is this plus this? Well, it's half of all of these intersecting segments. And so if we sum these two together, we have PA and PD combined to get AD, PB and PC combined to get BC. And so summing these two inequalities, we can get AD plus BC on one side and AC plus BD on the other. So these two triangle inequalities come together to show that if we uncross the lines, then we're going to decrease the total length of the segments. We started out with AD and BC, and we ended up with AC and BD. Now, since we assumed the matching had a minimal total length of segments, we have a contradiction, and therefore there can be no intersections. Because the reason why we could decrease this minimal matching is because there was an intersection. So what we're showing is that if there is a minimal matching, it has to have no intersections. And that is exactly the matching that we're looking for. Sorry for going a little bit over. I'm happy to stick around and answer more questions. Next time we'll be talking about polynomials and algebra.